In this video, it gives you a brief introduction about what we're going to be talking about today. And I think some of the visuals are going to be really good to help you all understand. And so I'm going to transition over to this video.
In this video, we'll be learning about the normal distribution and the 68-95-99.7 rule. When we talk about normal distributions, we refer to data we get from a population or sample. So before we actually talk about the normal distribution, we need to first distinguish the difference between a parameter and a statistic. A parameter is a number that describes the data from a population, whereas a statistic is a number that describes the data from a sample. Examples of parameters and statistics are the mean and standard deviation. But because of the definitions we just talked about, we have to be very careful with what symbols we use to represent these numbers. When we are dealing with a sample, we use the symbol x bar to represent the sample mean, and we use the letter s to represent the sample standard deviation. These are statistics. When we are dealing with a population, we use the Greek letter mu to represent the population mean, and we use the Greek letter sigma to represent the population standard deviation. These are parameters. The population parameters mu and sigma are very important when we talk about normally distributed populations. So what is a normal distribution anyways? A normal distribution is a special type of density curve that is bell-shaped. For this reason, the normal distribution is sometimes called the bell curve or the normal curve. The normal distribution describes the tendency for data to cluster around a central value. In fact, this central value is the population mu, which is always located in the middle of the curve. So for any normal distribution, we can say that some data points will fall below the mean, other data points will fall above the mean, but most of the data values are located near the mean. The normal distribution and its shape actually arises from many different variables found in nature, such as weight, height, volume, blood pressure, and many more. This is why the normal distribution is commonly studied. For example, exam scores are known to follow a normal distribution. Some people do great on exams, some people do poorly on exams, but a large majority of people score near the average or the mean. In this example, the average exam score is 50 because it is located in the middle of the curve. Now that you know what a normal distribution looks like, we need to talk about the population mean mu and the population standard deviation sigma. Both of these tell us important information about how the normal distribution looks. We'll talk about the population mean mu first. The population mean mu characterizes the position of the normal distribution. If you increase the mean, the curve will follow and move towards the right. And if you decrease the mean, the curve will still follow and move towards the left. This happens because the data will always cluster around the mean in normally distributed populations. As a result, the value of the mean determines the position of the normal distribution. On the other hand, the population standard deviation sigma characterizes the spread of the normal distribution. The larger the standard deviation, the more spread out the distribution will be. And the smaller the standard deviation, the less spread out it will be. Notice that when the spread increases, the curve gets much flatter, and when the spread decreases, the curve gets taller. The reason for this is because the normal distribution is a density curve, and the total area of any density curve must remain equal to 1 or 100%. So changes in the width of the curve must be compensated for by changes in the height of the curve, and vice versa. Overall, here are some points about the normal distribution. The normal distribution is unimodal. This means that the distribution has a single peak. The normal curve is symmetric about its mean, so you can clearly see that the distribution can be cut into two equal halves. The parameters mu and sigma completely characterize the normal distribution. The population mean mu determines the location of the distribution and where the data tends to cluster around. The population standard deviation sigma determines how spread out the distribution will be. The notation given to a population that follows a normal distribution can be written like this. Although it looks scary, it means what it says. For the variable x, it follows a normal distribution and has the mean mu with a standard deviation of sigma. Now that you've been introduced to the normal distribution, we can talk about the 68, 95, 99.7 rule. If we were measuring the heights of all students at a local university and found that it was normally distributed with a mean height of 5.5 feet and a standard deviation of half a foot or 0.5, we can construct a normal distribution as follows. From here, we can create intervals that increase by the standard deviation. So we'll have 6, 6.5, and 7, and on the other side, we'll have 5, 4.5, and 4. So what the 68, 95, 99.7 rule says is that within one standard deviation away from the mean, it contains a total area of 0.68 or 68%. Because of this, we can say that 68% of the population are between 5 and 6 feet tall. And if you go 2 standard deviations away from the mean, it contains an area of 95%. This means that 95% of the people in the population have a height between 4.5 and 6.5 feet. And finally, within 3 standard deviations away from the mean, it contains a total area of 99.7%. This means that for the population we are studying, 99.7% of the people are between 4 and 7 feet tall. Now you might be wondering, what happens if we go 4 standard deviations away from the mean, or 5 or 6 standard deviations away from the mean? And to answer that, you actually can. A normal distribution actually never touches the x-axis. It continues on to infinity. So you can go as many standard deviations away from the mean as you want, but the area contained within these regions will be very, very small. The 68, 95, 99.7 rule is a great way for approximating the areas of a normal distribution. And this works for any normal distribution, no matter what shape and size. So let's do some practice questions. Feel free to pause the video at any point so you can try these questions for yourself. Question number 1. The normal distribution below the video at any point so you
Okay, so I do actually want to pause the video. We might come back at the end and talk about a couple of those, but we are on chapter 6, section C, and the topic is the normal distribution. Taking out the chats and making sure no one needs anything. So this is kind of the last step into what you need to know to complete your statistics project, because it's going to ask you to interpret your data. And one of the questions that asks you in your statistics project is, in your project that you're doing, what is the standard deviation and what does it mean in your problem? And so as that video was talking about, when we talk about standard deviation, we talk about the normal distribution. Talk about the normal distribution of things. And so the normal distribution is symmetric, which means it's about the same on the left as the right. If you fold it in half, it's going to be on top of each other, I guess. It has a bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution, and its variation is characterized by the standard deviation of the distribution. Another name for the distribution is the bell-shaped curve. I think that people have gotten away from doing this, but when I was in college, especially, we would have teachers that told us that they did their grades according to the bell-shaped curve. And what that meant was, to me as a student, it meant that it was very unfair. Because what they were saying is, well, here's our normal distribution, this is our bell-shaped curve. So what the teacher was saying was that they wanted about everybody, a lot of people should be making a C in their class. So, which could be good for people and it could be bad for people, but it could be really good for you if you made all Fs on your test, but everybody else all made Fs on their test. So the teacher adjusted the grade so you made a C. The people that it could be bad for is the people that tried really, really hard and they made an A, but maybe they didn't make the top A in the room, because what this teacher is saying, who uses a bell-shaped curve, is saying that if this is the number of students, talking about the number of students who make A's and C's and let's say F's. Now B's and D's are along the same lines here, but they only want a few students to make an A. So even if you made an A on every test, if you didn't make a high enough A, you could be bumped to the next grade, which would be a D. So they wanted to make their grades fit this bell-shaped curve. So it didn't really matter what your true grade in the class was. They were going to force it to fit this curve. And again, if there were a lot of people that made F's, that could force them to make B's and C's. So it could be good for this end of the scale, but it could be bad for the front end, that people that would normally make an A. So this distribution arises quite frequently and describes many data sets concerning human characteristics. Okay, we have an example down here. This first one is describing chest circumference of Scottish militiamen in inches. And we've got the frequency over here. And if you kind of look at this and we were to draw some kind of curve over the top of it, kind of goes up, and it comes back down. Pardon me, this kind of models the normal distribution, pretty symmetric, okay? However, when we look at this one, we start up here, and it goes this way. This is talking about population density of 50 states. So this one is actually not a good representation of a bell-shaped curve. If we were to talk about this distribution, we talked about this in 6B, it looks like there's more data on the left. And so we would say that it's the opposite of what you think. We would say it's skewed right. So when there's less data on the right, this one would be skewed. So this one is a pretty good description of what a normal distribution looks like. It's pretty symmetric. And remember that another name for normal distribution was the bell-shaped curve. And this distribution is not normal. We would say it is skewed with more data on the left, so it is skewed right. So it says, which of these distributions appears to be normal? So I would definitely say, if I had to choose between the left and the right, that this one would be my normal distribution. This one appears to be more normal. It goes up and it comes back down in the same curve. It looks pretty symmetric. This one does something like this. Again, it looks like there's more data to the left here. It's not a terrible distribution, but it is skewed a little bit to the right. Okay, so this is the one that we would say is normal. So what is normal? In general, any quantity that is the result of many factors is likely to follow a normal distribution. For example, adult heights, scores on SAT tests and IQ tests, sports statistics. So the conditions for a normal distribution, what do we have to have? A data set that satisfies the 4 criteria below will likely have a nearly normal distribution. Most data values are clustered around the mean, giving a well-defined single peak. So when we're talking about that, this mean, our mean here would be this 0 value right in the middle, and it looks like we have the highest number right here at our mean. Data values are spread evenly around the mean. It has symmetry. So in other words, You look at this, we've got about this, if we fold this in half, would have done better if I had have drawn a more straight line. Let me go back and do that again. Look at this. We fold this in half. If we're folding it right here on this line, we have about the same information on the left and the right. That has symmetry. Tapering tails on each side. So the tails are the part, so it should get smaller and smaller and smaller. That's tapering on each side, to the left and to the right. It gets smaller and smaller and smaller. Okay. Individual values result from a combination of many different factors, such as genetics and environment. So, example 2. Which of the following variables would you expect to have a normal or nearly normal distribution? Okay, so, I'm going to let you type this in the chat. So, what I want you to pick is which one. You can either type just one or two. You don't have to type the whole thing in chat, but which one would you expect to have a more normal distribution? The scores on a very easy test, or the foot lengths of random sample of adult women? So you'll type number 1 if you think that the scores on a very easy test would give you a normal distribution, or number 2, you would type for foot lengths of a random sample of adult women. So I have one person saying 1 and 2 people saying 1 and 3 people saying 2 at this point. So if typically, if I, as a teacher, give a very easy test, I typically have a lot of people that score 100 on that test. And so if we have a very easy test, we have a lot of hundreds, and then it might go down from there. But this would be an example of a distribution of scores on a very easy test. Okay. So I would say that that is not going to be our normal distribution. That is, we've got more data on the left, so that's skewed right. The foot length of a random sample of women. I think most, I'm going to put shoe size here. I know that's not exactly the foot length, but most women tend to wear a 7.5. So I do think if we took a survey of just a random sample of women, it's probably going to be more along this middle, and then the people that have shorter or longer feet are going to be kind of spread out evenly. I think that this one tends to be more normal. Okay. Test scores on a very easy test, you're going to have tendency to have more people score high on that kind of test. So that's going to be not a value, not spread out like it should be. So we characterize the variation of any normal distribution, which is one single number, and that's called the standard deviation. So there is a very important rule, and it's called the 68, 95, 99.7 rule for the normal distribution. And what this rule means is that about 68%, or if you want to be really precise, 68.3% of the data points fall within one standard deviation of the mean. We're going to go over what this is in more detail in just a second. About 95%, or to be precise, 95.4% of the data falls between two standard deviations of the mean, and about 99.7% of the data points fall within 3 standard deviations of the mean. We've got a chart down here. So on our chart, I'm kind of use my highlighter here. It will let me. This section right here, darker green, this section right here in the middle, here's my mean. You can see that the mean is right here in the middle. And then we've got these, this dotted line right here, dotted line. And we've subtracted one standard, so the mean's right in the middle. We've subtracted one standard deviation to get here. We've added one standard deviation to get here. And what it's saying is in this dark green area, 68% of our data points are included. Okay. If we are to extend that out 2 standard deviations, we'll talk about this next section. So now we have taken and said, from the mean, we're 1, 2, we would have subtracted 2 standard deviations to get to this, and we would have added 2 standard deviations to get to this line. So between these 2 lines, we have 95% of the data points. And then if we were to carry this out to the very last little section right here, little bitty tails right here, that we carry it out there from the mean. This is 1, 2, subtract 3 standard deviations, and 1, 2, add 3 standard deviations from the mean. That at that point, we will have included 99.7% of the data points. So almost everything lies in between those 3 standard deviations from the mean. So let's talk about what that means in a real world problem. It says each test that makes up the SAT is designed so that its scores are normally distributed with a mean of 500, the score 500, and we have a standard deviation of 100. What does this mean with respect to the 68, 95, 99.7 rule? Draw a picture. Okay, so we already have a picture here. So what does, let's see, this is going to be our mean right here. The people get a 500. So to get 1 standard deviation, remember that our standard deviation is 100. We would add 100. So 500 plus 100 would be 600. And then to go backwards, we would do 500 minus 100, which is 400. So this is 1 standard deviation. And remember that 1 standard deviation from the mean is 68% of the data points. This problem, what that means is that 68% of the people who took the SAT scored between 400 and 600. Okay, if we go out to 2 standard deviations from the mean, now we're going 1 more. So this is 300. We're subtracting 100. I'm sorry. And then if we go 1 more this way, that's going to be 700. In this problem, 2 standard deviation is, we're using the 68, 95, 99.7 rule. So 2 standard deviations is 95% of the data. In this problem, what that means is 95% of the people taking the test scored between 300 to 700. So almost everybody got a score from 300 to 700. If we were to go 3 standard deviations from the mean, okay, so now we're going subtracting 100 again, getting 200, adding 100 and getting 800. That is, again, we're applying this rule at 68, 95, at 99.7. So is 99.7. So when we have 99.7, that's virtually everybody, right? 98.7% of the data. What that means is, in this problem, 99.7% of the people taking this SAT scored between 200 to 800 points. They're a very, very small amount of the population that was scored outside of those. That's what that means in this problem. Let's look at example 4. Detecting counterfeit coins. Vending machines can be adjusted to reject coins above and below certain weights. So you probably have put a coin in a vending machine and it spit it back out at you. It could have done that for various reasons, but one of the reasons is because your coin didn't fall in a certain weight that it was supposed to be for a nickel or a dime or quarter. So the weights of legal U.S. quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.0700 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what is the percentage of legal quarters that will be rejected by the machine? Draw a picture. Oh, I'm fixing to sneeze, I think, sorry. So here we go. We've got, it tells us what our mean is. It tells us it's 5.67. This is the weight of a quarter. Now this is in grams. Okay, so remember that we are supposed to look at what happens when we've got one standard deviation. So let's figure out what one standard deviation would be. They tell us that the answer, one standard deviation, is 0.00. That is one of the reasons why you need to put the zeros there, because I almost read that wrong. And so those extra zeros kind of help me to figure out. And not lose my place value. So 0.0700 grams is one standard deviation weight. So if I want to figure out what 68% of the things that would be included, I would need to add that number and subtract that number from my mean. So I would need to take 5.67 plus 0.0700 grams. I want to answer there. This is going to give me 68%. And then I want to also do 5.67 minus 0.0700 grams. Now you can leave the front zeros off and the back zeros off if you want to. It just might help you keep up with it a little bit better if you include them. So we've got 5.74 here. And when we subtract, we've got 5.67. So when we go out, one standard deviation this way would be our 5.6. Go one standard deviation this way, we are at 5.74. So that's 68% of the amount of points. Okay. Let's look at what happens when we do two standard deviations, because what they want us to know is if the vending machine is adjusted to reject quarters that weigh more than 5.8 and less than 5.53 grams, what percentage of the legal quarters will be rejected? Okay, so they're wanting us to figure out .53 to 5.81. This is what we're kind of looking for. So at two standard deviations, we would have 5.67, which is our mean, and we would want to add 0.00700 twice. We could also just multiply this by 2. We would also want to subtract it twice. Okay. And if we're two standard deviations away, this will tell us what numbers what amount of grams we're in between. So 5.81 is our upper end, and then 5.53 is our lower end. So 5.53. Another standard deviation here. This is going to be 5.81. Those look very familiar. So remember, two standard deviations give us our 95% of our data. So looks like these numbers look very familiar to what we're looking for now. So that means that 95% of our data falls in between here. Now let's make sure that we're answering the question. If a vending machine is adjusted to reject quarters that weigh more than this and less than this, what percentage are we rejecting? So if they weigh in this range, which is 95%, weigh in between 5.53 and 5.81, we are not rejecting them. So we are not rejecting 95% of them. But if they lie outside this range, we are rejecting them. So we would need to do 100 minus 95, or 100% minus 95%, and that would give us 5. So we are rejecting 5% of the quarters are being rejected. If they lie beyond two standard deviations. Now they don't want to do exactly whatever the mean is, because coins can get scratched, or they could have goop on them or something that makes them weigh more or less. And so that's why they considered this two standard deviations away. They know it might not be exact, but that's why they want to look at that two standard deviations away. So consider an exam taken by 1,000 students for which the scores are normally distributed with a mean of 75 and a standard deviation of 7. So they're telling us we've got students that are taking scores. The mean or the average score is a 75, and our standard deviation is 7. Okay, this is just another symbol for standard deviation. They want us to look at this. Now we've got a chart down here. So on our chart, let's fill this out. So these are scores. The mean is at a 75. So if I want to know what one standard deviation away is, I'm going to take 75 and I'm going to add my 7. That's what they told us that we had, a standard deviation of 7. And I'm also going to take 75 and I'm going to subtract 7. So 75 plus 7 is going to give me 82. And 75 minus 7 is going to give me 68. So these numbers will be 68 and 82. So that means that 68% of the students scored between a 68 and an 82. Now, if I look at two standard deviations, which is 95% of the students, I want to add my standard deviation twice, and I also want to subtract it twice. So this is going to be 89, and this is going to be 61. So these are 61 and 89. In this problem, that means that 95% of my students made between a 61 and an 89. Okay. And then if we want to look at 3 standard deviations away, remember 3 standard deviations away is 99.7. We would do 75 plus 7 plus 7 plus 7. And then we would do 75 minus 7, minus 7, minus 7. Now, the easier way obviously would be 75 plus 3 times 7. 75 minus 3 times 7. And you're welcome to do that if you would like to do that. 75 plus 3 sevens is going to be 96. And 75 minus 3 sevens is going to be 54. So 54 and 96. So 99.7% of the students who took this test scored between a 54 and a 96. Okay, here we go. We've got to work some problems with this. I am going to be asking you for your input here because some of these you really have to think about, and I want to make sure that you are able to kind of think about the answers to these before you leave. So it says, suppose we want to know how many students scored above 82%. What does the 68, 95, 99.7 rule tell us? Okay, so above 68%. So don't let this 68% confuse you right here. 68% would be right here. So if they scored above 68%, we're talking about everybody who scored 68%. We're talking about everybody who scored from here over. Okay. From here over. So we've got this part of the tail here that doesn't get counted. These people where did I get the 68%? I'm so sorry. I think I just read the question wrong. Hold on. Let me erase that. That's my fault. I apologize here. Suppose we want to know how many students scored above 82. And maybe I did read it wrong and then my brain did something crazy. Who knows? But 82 would be right here. This is our 82. So we want to know the number of students who scored above 82, which is this little part of our tail. This little section in here made an above 82. So let's talk about that. How would we figure that? How would we figure that out? Okay. What do I know about this little section of this tail? One thing I know is that if I look at this section here, now it doesn't ask me to, but if I am asked to include this section here, okay, these two little end tails, that I will have the only people I would have taken out were the middle that are 68. Okay, so this whole thing should be our 100%. But we're removing 68, and then we're only looking at half of those that make above that. So if I do 100 minus 68, we do 100 minus 68, we're going to have 32. Now that's 32%. Now, when I just did that calculation, I subtracted out this middle section. So I still have this whole section over here and I have this whole section over here. But we don't want to find out that whole section, right? We only want half of that section. So we need to do 32% divided by 2. And 32% divided by 2 would give us 16%. And so the people who made higher than an 82 is going to be 16%. Suppose we want to know how many students scored below 61. That's what I have. So this time we're looking for the number of students who scored below 61. So I always go over here and think 61 is right here. And I say, well, below 61 would be these people right here in this little X, below 61. There's also a little section over here that I'm going to look at that matches it. Because what you want to do is you want to start out with your 100 and you want to subtract, mark off the two sections that are identical, below 61 and then above 89. And then you want to subtract off whatever section is not included here. So it looks to me like between this line and this line is our 95%. So we would be 100 minus 95%, which would give us a 100%. I'll put my percents in there. 100% minus 95% is going to give me 5%, which would include both of these little tails. But we only want the people who scored below 61. So we don't want both of the tails. We just want one of them. So we would divide by 2 and we would get 2.5%. Okay. That's the answer to that. This can be a little bit tricky. The 68, 95, 99.7 rule applies to data values that are exactly 1, 2, or 3 standard deviations from the mean. The number of the standard deviations value lies above or below the mean, its standard score, or its z-score, abbreviated by the letter z. The standard score for the mean is called the z-score. The standard score for a data value that lies 1.5 or 1.5 standard deviations above the mean is 1.5. The standard score for a data value that lies 2 standard deviations below the mean is -2, which just makes sense, right? It's 1 standard deviation above the mean. It's a positive 1.5 for your standard score. If it's 2 below, it's a -2 for our standard score. So how do you compute a z-score? You take your data value minus your mean, and you divide it by your standard deviation. So we are going to calculate some standard scores here. The standard Binet IQ test is scaled so that scores are normally distributed with a mean of 100. So it's telling us we have a mean of 100 and a standard deviation of 15. So this is our mean. This is our standard deviation. It's telling me that in the problem. Okay, they want me to calculate the standard score for somebody who has an IQ of 85. They want me to do the same thing for someone who has an IQ of 100. And I think I'm going to let you guys handle the last one on your own. But after I show you 2 of these, so standard score of 125. So what you do is you take this take your score of 85, which is your data value, and you subtract your mean, is 100, and then you divide it by your standard deviation of 15. So you want to, you can type this all in your calculator at once. If you type it in that way, then you need to make sure that you're using alpha y equals and typing it as a fraction. Or you can find the answer to the top, which is 85 minus 100 is 15. And then you want to divide it by the bottom. So negative 15 divided by 15 is negative 1. Okay. If I want to find the standard score, so the standard score of somebody who has an IQ score of 85 is their standard score is a negative 1. Okay. So that means that they're below the mean. So if they have an IQ score of 100, I would take this 100 minus another 100, that's the mean, divided by my standard deviation. So we would have 0 divided by 15, which is 0. So that person is right in the middle with their IQ score. Their standard score is a 0. Okay, what do you guys get on the standard score if that person has an IQ of 125? Let you respond in the chat to that. Want to take your standard score of 125 and subtract your mean and divide it by your standard deviation. What is their standard score going to be? So what is the answer to that calculation? We took our standard score of 125, not our standard score, sorry. We took an IQ score of 125. We're subtracting the mean of 100 and dividing by the standard deviation of 15. And this, what we get is our standard score. What are we going to get? 25 divided by 15. Yes, it's approximately, I mean, if we round about 1.67, but yes, that is correct. Okay, so that's going to be our standard score. Now, let's look at these next ones. It says, once we have the standard score, we're almost done with this section. The properties of the normal distribution allow us to find its percentile in the distribution. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to. A data value that lies between two percentiles is said to lie in the lower percentile. For example, suppose you scored in the 45th percentile on the SAT. This is interpreted as 45% of the SAT scores were lower than yours, or you scored better than 45% of those taking the SAT score. You also can say that 55% of the scores were higher than yours, or 55% of the test takers scored higher than you. So they want us to find the z-score of 1.6 on the table. The corresponding percentile is 94.52. So we have a table that has z-scores right here. This is what they're talking about. So 94.52, you look at this table, is right here. That's your percentile. This is your z-score. So up here it says 94.52% of the data values fall below a z-score of 1.6 in a normally distributed data set. 95.52% of the values have a z-score less than or equal to 1.6% or 1.6 in a normal distribution or normally distributed data set, and a data value with a z-score of 1.6 lies in the 94th percentile. Okay, so those are just different things that we could say about this. So let's look at this. This is the last example we have today. Cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. In what percentile is a 20-year-old man with a cholesterol level of 190? So what we know is that we have a mean here of 178. We have a standard deviation of 41. And they want us to find the z-score that will help us find the percentage, okay? And so we're working this problem just like we did these up here. We're looking for our standard score. And they're telling us that we have somebody that had a cholesterol score of 190. So you do 190 minus your mean of 178, which is what they told us, divided by your standard deviation. You're going to get 12 on the top, 190 minus 178, 41 on the bottom. When you divide these two, you get 0.2926. We would round that to approximately 0.29. Okay. And what we're going to want to do is we're going to want to go to our table. So 0.29, here's 0.25, and here's 0.30. 0.29 would fall in between those. So we would want to round up, pick the one that is the closer value, 61.79. So I've looked for 0.29 on the table. We round it up to 61.79. That's the percentile. So 61.79%, which is the 62nd percent. Second percent. So if we go back and look at the interpretation of that, instead of saying 94.52, we're saying 62% of the data values fall below a score of 0.29 in a normally distributed data set. 62% of the values have a z-score less than 0.29 in a normally distributed data set. And a data value with a z-score of 0.29 lies in the 62nd percentile. Look at B. What cholesterol level corresponds to the 90th percentile, the level at which treatment may be necessary? So this time they're telling us that we have the 90th percentile. To find the state, we don't know what the value is. We're looking for this, what value we would have that correspond with that. But so I'm putting an X there for a variable. We do know we have a mean of 178 and standard deviation of 41. I'm going to go to my table and I'm going to look for the value that is the 90th percentile or closest to the 90th percentile. And there's 90.32. So I'm going to use, that was 1.3. That's the value that I'm going to use here. So let's work this problem. We're looking for x. No, we don't use algebra a lot here, but we can here. So we're going to have to. You're going to need to get rid of the 41 on the bottom of the fraction. So I'm going to multiply both sides by 41. 41 divided by 41 is 1. So those cancel out because they turn into a 1. 1.3 times 41 is 53.3. We're almost done. We need to solve for x. So we're going to add 178 here to both sides of our equal sign. And we're going to get 53.3 plus 178 is 231.3. And that is what cholesterol score you would have that's going to correspond to the 90th percentile, 231.3. So your homework is going to go through several of these concepts. I do want to go back to the video just really quick to see if you can remember how to respond to the first question in the video. And then we're going to transition over to talking about the project. I'm going to go back and make sure that you know where that is, how to find it. And you've got 2 weeks left to do your project. It's due November the 6th. So you want to make sure that you are making way and how to, and marking off parts of that project, okay? So I'm going to share one example on the video with you. Let's just see if you can come up with the answer here.
You can try these questions for yourself. Question number 1. The normal distribution below has a standard deviation of 10. Approximately what area is contained between 70 and 90? In this question, we know that the population mean is equal to 70 because it's in the center of the distribution. We also know from the question that one standard deviation is equal to 10, and we can see this because each interval goes up by 10. According to the 68, 95, 99.7 rule, we know that there is an area of 95% contained within 2 standard deviations of the mean. 2 standard deviations to the right gets us to 90, and 2 standard deviations to the left gets us to 50. According to the 68, 95, 99.7 rule, this means that there's an area of 95% contained within this interval. However, we are only interested in the area from 70 to 90. So dividing this area by 2.
All right, so we're only interested in this section here. This whole thing is 95%. What is it? What is the answer going to be if we're only looking for 70 to 90? You can respond in the chat there. $95 divided by 2 is 47.5. So that's what area they're talking about. Okay. So let's go to our really quick. Let's go to our project and go over some of the things that are on our project. I'm going to go back to Blackboard for just a minute, just to make sure that you know where it is. So hold on one second.